Alright, so this tutorial is a continuation of a discussion today on radioactivity and rates of decay. We've established that radioactivity is a spontaneous emission of radiation from an unstable nucleus that doesn't happen all at once, but rather monotonically, one by one by one, but at a completely random rate. So what we want to look at is the mathematics of the probability of this decay, and to be able to essentially calculate, quantify how much of a sample you'll have left after a certain period of time. We're going to look at it fairly simplistically in terms of half-life. We're not going to go into too much of the actual equation, but we'll mention it. Okay, so let's start off with the basic equation that we are going to use for this, and which basically tells us at the rate at which something decays. So when you have a radioactive material, we can look at the decay rate, delta N over T. And that's going to be equal to negative indicating a decreasing amount over time, lambda times N. Okay, where delta N over T is called activity. Okay, as in radioactivity. It is the rate of decay. It is generally in counts per second, amount per second. The metric unit is the becquerel, BEQ, but we're not going to use that too much. But just be aware that we can look at how quickly something's decaying as a function of the number. Lambda is not wavelength. It is called the decay constant. And what you want to know about that for now is that it is a fundamental property of the nucleus. It is completely independent of temperature. It is completely independent of the surroundings. It's even independent of the amount of the sample you have. It essentially is the probability, or it's a measure of the probability that a nucleus will decay in a certain amount of time. There's nothing definite about it, but we can quantify that. And then N is the number of the original nuclei still present after a certain amount of time. Okay, so sometimes we'll get as a whole number or even as a fraction. So let's interpret this equation and see what this tells us about decay. First of all, if you were to solve this equation for how much N is left after a certain amount of time, you would require calculus. You'd have to do integral calculus, and you're not responsible for that. But it's worth looking at this equation. What this would tell us is that N, the number of particles of the original, okay, not the decayed ones, is equal to what you started with. And then we would have an exponential, negative e to the negative lambda t. Okay, and so the lambda we'll talk about is important for determining how quickly something's going to decay, but we see that as time increases, N is going to decrease in a nonlinear fashion. Okay, in fact, it decreases exponentially. You might recognize that from pre-calc or calculus. Okay, so we're not going to have to solve any problems with this equation specifically, but it gives us some insight about how a sample will decrease with time. Right, the next point we want to make is that since the activity, right, this whole term is proportional to N, okay, lambda is always constant, the activity itself will decrease with time as well, and it is an exponential decrease. So we can make plots of how many nuclei we have left after a certain amount of time, and or we can look at how quickly it's decaying as a function of time, and it follows not exactly the same curve, but the same shape curve. It's an exponential drop. So to summarize, N drops with time exponentially, activity drops exponentially with time, lambda does not change whatsoever. The probability that decay is going to occur, which lambda again is an indirect measure of, is going to stay the same. Alright, the decay, or excuse me, the greater, now what lambda can tell us indirectly as well, is that the greater the value of lambda, the higher it is, the more radioactive the substance is. Okay, basically it's telling you it's going to decay fairly quickly rather than fairly slowly. Okay, so the faster it decays. And that's, again, a conceptual idea that you want to understand. So lambda determines how quickly it decays, and the faster it decays, generally the more dangerous it is. In other words, if you have a sample of something that is very radioactive, that means it decays very, very quickly. Okay, my writing is just deteriorated. Now, of course, there is an upside, if you will, to having a high decay rate, in that the amount of radioactive material you have after a certain amount of time will drop much faster than a slow decay one. But if you're getting exposed to radiation at a very acute rate because you're having a lot of counts, then it's generally more dangerous. Okay, so let's turn our attention to half-life, the mathematical concept that we will be tested on and expected to know. So half-life, by definition, and it's pretty much in the name, is the time, okay, that's the life part, it takes for half of the original parent nucleus to have decayed. Half-life is directly related to lambda once again. It is roughly equal to 1 over lambda. Okay, the actual equation, which we won't derive, is the natural log of 2 divided by lambda, but essentially as lambda gets bigger, the half-life gets shorter. It's more radioactive. So from the lab you did with the dice, you should have produced a curve that looks like that, a nice exponential. And one of the things we would want to look from the curve, at least very simple, is how much time it takes for half the sample to drop. So if I go down to, I have 100% here, we go down to half, we go over the curve, we drop, this would be tau, or t, half, that would be our half-life. And then you can see with the successive ones, we go a quarter, that's 2 half-lives, an A, 3, a 16th, 4, and so on and so forth. And in theory, you never get down to 0 radioactive nuclei left. It's always, it's half and half and half. But for all intents and purposes, when you get down to, let's say, a few thousand nuclei, that's essentially nothing compared to the billions you might have started with. You don't have to know half-lives, but I've included 4 here because they have some significance in various applications. Carbon-14, so we see 5,000 years. Tritium, only 12 years. Uranium, now we're talking 4 billion years. Plutonium, 22,000 years. I could have put, I was thinking of doing that, I guess I mentioned now, there's an isotope of iodine, iodine-131, which is on the order of days. And there are some isotopes that decay in seconds or fractions of a second. So the reason I put these on here, you've heard of carbon-14 before, especially in biology. This half-life is particularly important, the time, as well as the fact that it's carbon, for dating. Okay, carbon dating, you may have heard before. Okay, and dating of, and I'm not going to write all, of organic materials. So if we discover, let's say, an ancient civilization, prehistoric, where there's been a fire and there's burnt wood, that wood is going to have carbon-14 in it, a certain percentage compared to the normal carbon-12, and based on the rate at which it decays and how much is left in that sample, we can determine how old it is. It's a little more complicated than that, but it's a pretty straightforward process. Tritium we've mentioned before because that is the fuel for fusion, or one of the key fuels, and because of its short half-life, it can't be stored. Okay, so you don't find this, and you do find it a little bit in nature, but it's not going to be around long because half of it's going to be gone in 12 years. So we generally have to just keep creating it. All right, uranium-238, 4.5 billion years. That may sound familiar. That's essentially the age of the Earth. So we can date very old ancient rocks to get an idea of how old the Earth is. And uranium-238 is the key one. Plutonium-239, that's associated with nuclear bombs, nuclear waste. So even if we wanted to just, let's say, get rid of all our plutonium bombs, Russians, the US, other countries, and bury them away, they're still going to be highly radioactive for 22,000 years and another 20,000 years. So it'll be 50,000 years or so before the activity has gone down enough that you might consider it safe. All right, so let's look at the graph of this a little bit more, a problem, and we'll be done with this. Okay, so based on the graph below, how much of a 0.512 kilogram radioactive sample be left after 64 days, expressed as a percentage and as a mass. Alright, so we're not going to use that nice looking equation up here. Okay, we're not expected to. We're going to look in terms of half-life, and this is fairly straightforward, if not a little tedious. So let's first of all determine from this graph what the half-life is. So if you look closely here, this is counts per second, so that's really just activity A. Right, so we start off with a sample of 80, so we go down to 40, and we drop, and we see that our half-life is 2 days. Okay, so how much time are we talking about? 64 days, so I believe that's 2 to the 6th power, so that's 6 half-lives. I don't know if it's half-lives or half-lives, so 6 t-halves. So if we start off with 100% and we have that 6 times, I believe we will end up, I did the math earlier, I'm probably going to bungle this, I'm not remembering off the top of my head. I remember that if we have 0.512 8 times, that's 0.008 kilograms. Alright, so you have 8 grams left out of essentially 500 grams that you started with. Okay, so basically if we do 100 divided by 64, or 1 divided by 64, we get basically 1.5%. Okay, sorry about that. So we just had to do 100% divided by 6, d4, or 2 to the 6, so it's 1.5% left. Alright, what's the activity after 2.5 lives? Now here we're going to have to estimate more, so 2.5 half-lives mean we're going to have 40, then 20, that's 2 half-lives, and then half a half-life would be around 15, around that. So we go over and we see, oops, my bad. 1 half-life is 2 days, 4 days is 2 half-lives, 2.5 is that. So we're looking at about 15 becquerel. Okay, would the decay constant be relatively high or low? Explain. If you recall from up there, the decay constant is an indirect indication of how quickly it decays. So half-life of 2 days compared to some of these is very, very short, so lambda is going to be high. Okay, and then what percent of the original decay rate? What is the percent of the original decay rate if this is the sample after 4 days? Sorry, I can't talk. Well, 4 days is 2 half-lives. Okay, so if I go over to 1, 2, 4 days, I see that we are now decaying at about 20%. Alright, so those are some pretty straightforward problems with radioactivity and half-life.